All right. Well, good morning. Oops, let me turn this down. Okay, little feedback there. I've just got another camera on standby here if I need to do any homework review. All right. Are there any questions on the homework for today? Everybody looks like they have their microphones muted. So if anyone's talking, nobody has their video on. Well, almost nobody. But I'm not hearing any questions. So what I'll go ahead and do then is move on to that section that I did not cover, which was basically Bodie plots. And the reason that I wanted to talk about those in general is because when we go to graph our response, and I have been doing that response, right? I've been kind of drawing up the pictures and showing the shape of the curves, and they're always rounded. And there's also the assumption that I'm only focusing on one frequency, especially when I showed you the high pass filter and the low pass filter. So what I want to do, I'm going to go ahead and share my screen here. We can find, there we go, share. Okay. So what you're seeing is a graph. And what I set up here was a high pass and a low pass filter using similar components. And so that you end up with a point where you see those two curves cross. At that point, that is the cutoff frequency. So for one of them, it looks like a um, high pass and a low pass. So I guess what is that? Orange colored one here is my high pass filter, and the other one is the low pass. And you can see that these don't really look like the graphs that I was putting on the board. And part of that has to do with the compression aspect of it. So right now, this cutoff frequency is about 159 kilohertz. The scale goes all the way up to 1 megahertz. Because of the linearity of the scale, I basically see no detail down here close to zero for my high pass filter. You don't see that curve. If I were to change my scale, and it's a neat thing about using Excel is that it makes it kind of easy to do that, provided I can get my scale over here. So what I'm going to do is I'm going to change the maximum now, instead of 1 million hertz, 10,000 hertz. And when I do that, you can now see the high pass filter looks almost square. I still don't see anything down near zero. Oh, actually, no, it didn't change on me. Wait a minute, what changed? Oh, it changed. Oh, it changed to 10 million. Hold on. That's one thing about playing with Excel. There we go. So what you see now by moving that to 10,000, we still don't see a lot. We can see the slow, gradual increase of the high pass filter. Of course, the low pass filter is always giving me everything at that point. So on the linear graph, trying to play around with this and make everything fit in there and see everything doesn't work very well. And so what we end up doing, and let me go ahead and go back to my previous range of 1 million. So now we have that graph back. But what I'm going to do now is, you can see down in the corner here, I'm going to change it to a logarithmic scale. And when I do that, this starts to look a little bit more like the graph that I had before. Let me go ahead and change, now that I can see everything better, I'm going to change my cutoff frequency by, all I'm doing here is I'm just changing the size of the capacitor. It starts to look a lot more like the graph that I do. And that is because you look on the logarithmic scale, and now instead of changing a constant number of frequency units per unit, so if I go, before the scale had 200,000, 400,000, 600,000, 800,000, and a million, now the scale is changing by a factor of 10. So I start here with 1, and then I have 10, 100,000, 10,000. And what that allows me to do is see a lot more detail all the way across. And this becomes even more important if I were to have a graph similar to the response curve that we had for our amplifier, where I had two different cutoff frequencies. So if I'm trying to look at a cutoff frequency of, say, 20 hertz, that's down here. And if I want to show an upper cutoff frequency of 10,000 hertz on a linear scale, it'd be off the chart. On the other hand, if I'm looking at the upper cutoff frequency of 10,000 hertz, then you kind of see what I saw earlier, where I don't see any detail at lower frequencies because everything is compressed. And so the logarithmic scale for the frequency allows me to get a much better look at and see the changing nature of that slope. Now, that's half of it. The next step, and this is part of what we were doing last week when we were talking about using log gain or log decibel gain, that my output scale here is still linear. When I get way down here, it's like so close to zero, or over on the upper end, I can't really see what's going on. Now, I can change this to a log scale, very similar to what I did on the horizontal axis, by just clicking that. And now I have a lot better idea of what's happening. So we can see that we have a 1 here. This is 1 times 10 to the minus 1, which is 0.1, 0.2, I'm sorry, 0.01, 1/100th, and then down here, 1/1000th. And this is the part where the Bode plot really comes into play. We can see that once we get away from the cutoff frequency, this response becomes linear. And now we can get an idea of exactly how far that goes. Now, what I did here, of course, was I forced the left axis to be logarithmic. The beauty of doing the decimal, or I'm sorry, the log rhythmic, or no, yeah, decibel. Sorry, decimal decibel. I was doing that last week, wasn't I? By doing the decibel voltage gain, that makes that scale logarithmic to begin with. And I'm not going to try and show that on here. It'll probably be easier just to show it with I think drawing it, maybe, I don't know. But what we're going to do, so this would be the actual Bode plot. So you can actually see, if we were to zoom in here, this point right here is pretty close to 0.707, which for a decibel voltage gain is minus 3 dB. So negative 3 dB. You'll often hear me refer to cutoff frequencies as a 3 dB down point, minus 3 dB. You'll often hear me refer it to as a half power point. All of those are the same point, because if I take the decibel power gain of 1/2, that is minus 3 dB. If I take the decibel voltage gain of 0.707, that is also negative 3 dB. So the 3 dB down point corresponds to that. And since power is proportional to voltage squared, if you take 0.707 and square it, you get 1/2. And so all those points correspond to right there. And let me see if this is going to work for me here. Let's see. I can. I don't know if I can. Oh, there we go. Okay. Almost. Right. So let me see if I can. All right. So I'm going to stop my sharing here. Go to, I can make this the full screen. All right. Well, I don't know if this is working or not. Basically, what we're looking at here, if you look at my second one here, when we do our Bodie plot, the actual Bodie plot basically looks like, for a low pass filter, looks like that. So you've got that dip right here at the cutoff frequency of minus 3 dB. It's not too significant. And what we do instead, to make life easier, is do what is known as a ideal. This graph up here is so close to two straight lines that I'm just going to make my ideal Bodie plot 2 straight lines. You have your response during the pass region, and then you have your response in the cutoff region. The slope of that line, of course, minus 20 dB per decade. And the point at which those two lines intersect is, in this case, the upper cutoff frequency. So this is just my decibel voltage gain. So now what that gives me is a log versus log plot. So this is the actual response up here, where you have that rounding. Oops, there we go. You have that rounding right there. And this one is my ideal with the two straight lines. Any questions on that? That's the lesson. Right. Well, that's the part that I did not finish last week. I pick up from here in whatever section was next. Here. So he does have another section where he talks about more Bodie plots, where he gets into the frequency, or not the frequency, but the phase shift response, which I'm not going to talk too much about here. And after that, section 14.8 is the Miller effect, and that is where the recorded lecture picks up. And so the rest of that then covers the rest of that chapter. And you do have a take-home quiz. I've provided both a Word document as well as a PDF, whatever works for you to download and print, or just, fill out the sheet to turn in. That take-home quiz will be due at the beginning of class next week. We will also do quiz number 2 next week instead of this week. And so we'll do the quiz number 2 in class on MOSFETs at the beginning of class next week. I'll collect the take-home quiz, probably go over both quizzes at that point, and then start on chapter 15, which is our differential amplifiers. Any questions? Okay, if anybody is talking, I'm not hearing. Hopefully my volume is up enough. Anybody want to say something just to know I'm working?
No, I'm good, sir.
Okay.
Yeah, you had, so I thought on the or the modules, you would release something with chapter 16. Have you, I thought, didn't know whether you were skipping.
Chapter
You
2.
got quiz chapter 16 document, that's for module 5.
All right, go back to. Is that what I called the take-home quiz? Ah, yes. Okay, I see it. I never did. Yeah, in the old version, I want to say 2 editions ago, this was all chapter 16, and now it is chapter 14, and I never changed the name of that quiz. So usually I just print it out and give it, so you never see the name of it. But I will go ahead and change that. So apologize for that confusion, but I see why you had a question on that. So it is chapter 14 quiz. It is over the material that I cover in this week's lecture.
Okay.
Any other questions? No other questions? All right. Well, thank you for your time this morning. This will be recorded. I will put this up in place of the link for this. And that way, if you need to see it again or you want to see it again, you can. And then for anybody that wasn't here, you'll have a chance to see all that as well. All right. Well, everybody stay safe. I mean, I don't know what you're getting up there, but I'm barely getting anything right now. I think they might have, I don't know, overcorrected here, but better safe than sorry. All right. Well, with that, I will go ahead and end the meeting. Again, thank you. And we'll see you next week.